Good morning, Ohio.
おはようございます。
Ohio gozaimasu. 早安. Yeah. We're going to start this new experiment. We're going to start this year by teaching this course in 6 different places. Yeah. That's us here, Taida, National Taiwan University, National Yangming University, and Jingyi University, plus Tokyo Institute of Technology. And the other one is Guangdao, right? Guangdao. Okay. Okay. So this is the first lecture. I will give a first introduction to the whole subject, the introduction to HHT. This introduction will serve to cover everything. Okay. If you don't have time after you hear the introduction, you can leave. You don't have to come back anymore. But if you have time, I strongly suggest that you sit through the whole semester. The class. What's the commotion? Okay. And this introduction has a busy subtitle. The subtitle is the Introduction to HHT for Nonlinear and Non-Stationary Time Series Analysis. In fact, later we'll go way beyond time series analysis. We're going to come to image analysis or even multidimensional data analysis, but that will come later. But the most of the subject we discuss is time series analysis. And another subtitle is a plea for adaptive data analysis. This is I take this as a mission for me, because most of the data analysis methods that we use are not adaptive. We will get into the details later. Why we need adaptive? Because if you have a priori assumptions, then most of the methods that we use does not satisfy all the conditions. And only adaptive, you can actually fit your data to the particular data that you will have. When I say data analysis, I want to make it very, very clear. Data analysis and data processing are 2 different things. Yeah. If you go to any library, you will probably find hundreds, if not thousands, of titles. Yeah, they talk about data processing. In fact, most of the place that when they teach a course, they will probably teach data processing course rather than analysis. Now, I want to make it very, very clear. This course is analysis course, not processing course. Now, to make that clear, I have to make a difference. I have to present to you the difference between processing and analysis and analyzing. Yeah. Processing, this word data processing comes from the root word of process. Yeah. This process is a Latin word, and it comes from 2 parts. Pro means forward, cedere means to go. So the whole word processing in English implies that you just go forward. Why you want to go forward? Because put this together, that is a particular method to do something, some particular things. In other words, you have a prearranged, a pre-given, predefined algorithm. And once you take this algorithm, you put your number in, something come out. You don't have to think anymore. This whole processing does not imply thinking. Yeah, imply move forward, imply do something. So because of that, data processing usually give you mathematical meaningful parameters. Why mathematical meaningful? Because the algorithm is defined mathematically. It has nothing to do with the physical problem. For example, in Fourier analysis can be used anywhere. Yeah. Fourier, when they design Fourier analysis, do not have anything particular in mind, even though Fourier has the heat conduction problem in mind. But later you can use anywhere. And because it's defined so broad and so mathematically, so whatever you come out is a set of mathematical parameters that will help you understand the problem from a particular viewpoint. And that particular viewpoint is totally based on the algorithm you use. Analyzing is very different. Analysis is come from Greek. The root word is Greek. And it comes ana, means up and throughout. That means everything. And less means losing. And this put together means that you take anything, then you cut it in parts, totally cut in parts. And then you study the characteristic and property of each part. And also study the interrelationship between parts. So by the time you take something as whole and you cut in pieces and you study each pieces, study the interaction between pieces, then you thoroughly, you thoroughly understand this process. And that is analyzing. That is analysis. And because of that, data analysis, the emphasis is in physical understanding. We want to understand what this data is. And that's what we are shooting for. We are not teaching data processing. We are teaching data analysis. In the whole process, we have to think. We cannot just push a button, something appears. Okay. And we will emphasize this different more and more as we proceed. Now, data analysis. We agree we're going to do data analysis, or at least I decide to do data analysis. The data analysis, we have three questions. Why we do it? How did we do it? And what should we do? Why we do it, we have to justify. Why we have to analyze it? Why don't we just processing it? Okay. And in the past, how did we do it? Okay. We were going to answer these three questions in the introduction. First, we want to talk about the why. Why do we have to analyze data? Data are the only connection we had with reality. Yeah. If you talk about anything, what happened? We have an echo. Can you still hear me clearly? Hello?
Yes. Yeah.
Okay.
Yes, no problem.
No problem. Okay. Data are the only connection we had with reality. Anything you say, you have to prove it. You have to back it up. What do you back it up with? With data. And that's the one thing that you cannot argue with. Okay. For example, even if you have data, people still don't believe it. For example, global warming. Everybody knows that global warming is a big issue, then or weather is getting warmer, and then we have more hurricane, and the sea level is going to rise. Some islands are going to be totally submerged and all that. Everybody's talk about that. But is everybody believing global warming? We can present in data as over the last 100 years, the temperature increased by 0.6 degree, and you look at the sea level is rising. You look at carbon dioxide is rising. Even that, people still don't believe it. Because even a lot of people has preconceived the concept. And if you really want to prove that, you want to have more data and prove beyond doubts. And before that, people like George Bush still think that's no problem. Yeah, we have to wait and see. Yeah. So even we have this data to connect with reality, but then we have to analyze the data to find the truth. Data itself does not convey the impression. We can have thousands of data of temperature, And some place the temperature may increase, sometimes temperature may decrease. And you have to analyze the data to find exactly what to do. So if we find the truth, that will increase our understanding of the problem. Now, ever since the advances of computer and sensor technologies, IT technology, there is an explosion of data. I worked for NASA for 30-some years. The building that I work in has nearly 1,000 people. More than half of that are PhDs doing research. It's a huge building, you can imagine. But next to our building, there's another building, even bigger than our building. Has very few people. What are the building for? For data. There are racks and racks of these little cassettes, little tapes, and whatever. But as the technology improve, the storage media change, so these people in that building are busy changing format and how to have the best way to store it. And most of the data just stored there, and not many people use it. Yeah. Why? Because most of the manager, not only in NASA, anywhere, they can measure their achievement by how much data they generate or how many bits of data they generate. In NASA especially, if you have a satellite, and satellite will go out and keep on collecting data, and that's a success. Yeah, but to understand the data, to find out the truth, that's science. Science is a very tiny bit of the big operation like NASA. Yeah. So the data is very complicated, and there's lots of data. So in the past, we are thirsty for data. We look for data. Like at the beginning, I talked about this probability distribution. And I told you that the first probability density function of the wave profile took 2 months of a graduate student's time to digitize the wave profile and eventually create one distribution. But now we have computer, we have this advanced technology. In a few minutes, I can produce a probability distribution function better than the 2 months work that a graduate student produced. So data now is exploding. We have an explosion of data. And it's so much so that from a situation of thirsty for data, we're looking for data. Now, the data is just too much. And if you open up your mouth, you are almost like when you are thirsty, you're drinking out of a hydrant. Hydrant is what? It's the 救火栓. I mean, when you fight fire, you open up this hydrant, the water will just come out. Okay? But you're only thirsty. You only take a little sip out of that. Most of the data are actually wasted. Yeah. And even for the little bit data that we thought we understood, the understanding is very incomplete. Science. This is what Poincaré said. Science is built up of facts, as a house is built of stone. But accumulation of facts is no more a science than a heap of stone is a house. Poincaré is a very famous mathematician, scientist, philosopher. He's probably the last universalist. He understands almost everything related to science. It's French. What he said here is very clear. He says science is built of facts. Facts here are indeed our data. Yeah, our observation. Data can come in different forms. Yeah. It's just like we build a house with stone. But if you collect a mass of data, that's not science. Yeah. Just like you collect lots of stone, and that's not a house. A heap of stone is not a house, and a heap of data is not science. What is science? Science is understanding. Understanding does not come out from a simple processing. understanding come out of true analysis. So, therefore, if we look at the data analysis is the key step in converting these facts into the edifice of science. You want to build this house, you have to look at the stone, the right shape, the right place to fit in, and eventually becomes a house. And data is the same thing. If you want this data, these facts, to be part of science, you have to convert this fact into a part of the house. And that conversion means you have to put the meaning, infuse the meaning into this code number. The code number itself does not convey meaning. And not only that does not make you think clear, it even makes you feel dizzy. If I give you page after page after page of data and ask you, say, hey, look at this is my data. What can you find out? Nothing. You have to go through the data. You have to analyze data. Yeah. You have to let the data tell its story. Yeah. Somebody say, say not only tell a story, sing its own song. Yeah. The data has to be able to express themselves. Yeah. Data and data analysis are very important. It actually separates science from philosophy. What is the difference between science and philosophy? To me, it's data. If the philosophers can argue about something for years, for tens of years, for decades, for hundreds of years, for centuries, without any conclusion. Like, for example, a very typical problem in China, I don't know, any culture must have their own argument. In China, it's a big argument is whether people, when they are born, whether they are inert for good or they are for bad. Their nature is for good or for bad. This argument is going on for 2,000 years. No solution. Why? Because we don't have data. Even though data does not tell the whole thing, but still, without data, then you have... okay. Without data, you will never really reach a conclusion that it's indisputable. So, with data, we'll talk about science. Without data, we'll talk about philosophy. A philosopher can sit in a coffee shop, can walk in the woods, can talk about that. Science, we have to look at the data and analyze the data. And after we understand it, then that becomes part of our understanding, and that becomes a part of the truth. To me, collecting and analyzing, synthesizing and theorizing are the core scientific activity. What do we do as a scientist? Some scientists collect data, make observations. Yeah. Some people analyzing data. Yeah. Get all the data and make a story out of it. Once you take the data, once you make the story out of it, you have to synthesize different kind of data. You put it together and make a whole story. And then you have a theory. That's the core. Yeah. For example, as we know now, the Earth is not the center of the universe. Let's start from painstaking collecting data of Tycho. And he, day in and day out, he built a beautiful instrument at that time and observed all the planets. But he did not analyze it. He documented all the data. The analyzing will later be done by Kepler and Copernicus. Yeah. And those people analyze it. And those people not only analyze it, they synthesize it enough. Synthesize it, Kepler find Kepler's law. This is the Earth sweep through a orbit with the same area. That is synthesizing. That's some big advancement. But if you take Newton to make a theory, and when Newton have the theory, it's great. All right, we have inverse proportion of attraction force, square proportion of attraction force, gravitation, and that explains a lot. And then later we found that even that is not very good. Why? Because we collect more data, and data is better. So scientists keep on doing this, collecting data, analyzing it, understand it, synthesize it, and come up with a theory. And then another layer of theory come up again. This is our activity. So if in science, if you do not have data to prove anything, that's a hypothesis, conjecture. Yeah. And once you have that, then you will have a real theory or real science. So data analysis in this area, in this activity, data analysis is the key. You're collecting data, that doesn't count. You have to analyze it. Without analyzing, you cannot synthesize, you cannot theorize. So this is a key link in this activity. Because it's such a key link in the activity, it is too important to be left to other people. Here by other people, I mean mathematicians. Yeah. If data is so important, why should we let other people analyze it for us or do the analysis for us? And unfortunately, most of the people doing data processing really does not understand, sometimes even does not care about the science. In United States, at least I've seen, a lot of scientific research group has a small subset of data processing people. These data processing people, if you invite him in, say, so you're doing what? I'm doing data processing. What do you process? Oh, we got a lot of number. I go through this number, and here is the result. So what is this? He said, I don't understand what the scientists were doing. I'm only crunching numbers. They say crunching numbers. Crunching numbers is processing the numbers. And when you ask the scientists, so, what did you do? So, oh, we try to understand this based on this and that parameters. So how did you get these parameters? What's the details of getting this? So I don't know. We have a number cruncher. Okay? So that makes the research into different separate groups. And the key part of that is in the hands of other people. And that other people, they may be mathematicians, they may be not. But their method they use is totally mathematical. That's not the correct way of understanding science. One of the key toward discovery is that you have to look at the data. You have to know how the number come out of the data, step by step, without any exception. Because observation or data, there are a lot of pitfalls in there. If you do not understand the whole process, the likelihood is that you will never be able to find anything significant. So I maintain that data analysis is too important to be left to mathematicians. Then people ask me, so why? Mathematicians are smart people. Of course, mathematicians are very smart. But we have totally different agenda, totally different paradigm. Yeah. I put mathematician here and scientists and engineer in the other category. We're not totally antagonists, but we're not looking for the same thing. Mathematicians are looking for absolute proofs. Yeah. And the absolute proof they want. Once they prove it, that's it. You can never improve upon a proof. For example, we all studied the plane geometry. The plane geometry, the proof has been done more than 2,500 years ago. At least by then, Euclid has already summarized that into the book Elements. Yeah. That proof, it's so beautifully done. And even today, we cannot improve it. Because the proof is absolute. Yeah. And that proof is totally based on logical consistency. Yeah. The logic is so tight, so rigorous, and the mathematical method is so rigorous. That's what the mathematician lives on. Yeah. But we are very different. We are looking for agreement with observation. Yeah. We scientists, seldom you will find a scientist that proved something or observed something and interpreted something that will stand for 2,000 years. Very, very few. I read one book by Cravens, talk about the history of science. And at the very beginning, the introduction, he said that if we look for the most famous scientist, for example, Aristotle in Greek, and if in Greece, if we get him back here, we can teach him a lot. Not only we, a high school student can teach him a lot. At least we can tell them, listen, the Earth is not center of the universe, and we actually rotate around the sun. Not only that, Earth is a sphere, okay? And we know the roughly size of that, yeah? And we know how deep the ocean is. Not only that, we know that on the Earth there are Euro-Asian, African landmass, and there's another landmass of North and South America. We know the geometry. We know the not geometry. We know geography. We know general science. We know a lot. But a lot of the work that is summarized by Aristotle are more than 2,000 years, and that's gone. I believe 1,000 years from now, a high school student can come to us, can teach us something totally new and correct our concepts. But I bet 5,000 years later, if we awaken Euclid and let him sit with somebody doing geometry, I don't think anybody can teach him something dramatically new. Probably not. Yeah. So within that area, he's an expert. He's absolute. Yeah. There's no more improvement. But we cannot do that. We always look for approximation. Yeah. And we're looking for physical meaning. We look for approximations. We are not looking for exact science. Like, for example, among all of you, I believe most of you have used F equal to ma. Yeah. When we use F equal to ma, we say, well, that's perfect. That's great. Then Newton come up with this equation and solve everything. We use that to study static. We use that to study dynamics. Yeah, dynamics is not only solid, but it also study fluid. Fluid is based on F equal to ma. Navier-Stokes equation is derived based on that. Yeah, is F equal to ma right? Perfect. We send people to the moon and back based on F equal to ma. What's wrong with that? Nothing. Yeah, and everything we do almost is based on F equal to ma. However, if we think of relativity, then we find that F equal to ma is only an approximation. It's not right. From a mathematical point of view, it's absolutely wrong, because F equal to ma is based on a reference frame that's its inertia. The reference frame is not moving. It's stationary. Time is absolute, space is absolute. Relativity by Einstein told us time can warp, space can warp. The only constant is speed of light. Yeah, so that is the new improvement. Is that important to us, daily life? Most people think not, but indeed it is. But we don't feel it. Why it is important? Anybody has a GPS system will understand that relativity has to be important, because the satellite is swirling around at very high speed. And in that high speed, the time dilates a little bit. And day in and day out, your time will drift. And if you do not take relativity in consideration, you will never pinpoint your position to be within a few inches or a few centimeters or whatever. Okay? So, at that scale, the approximation is not working anymore. So when we find the approximation is not working, then we improve it. If it's not important for the approximation, we scientists and engineers, we don't care. This is this difference is very, very important. When I talk this to the, give this talk to the mathematician. The last time I give this talk to the mathematician was this January, past January. I was at Caltech. I give this, and they are mathematicians. I give the talk in the applied math department. I told them the mathematician is very different from scientist and engineer, and somebody take exception because applied mathematicians sometimes think they are scientists rather than pure mathematician. The way of thinking is very different. A joke that I read once in Physics Today talk about the difference between scientist and engineer and mathematician. They will talk about 3 persons traveling in Scotland. Yeah, they are all riding the train. A mathematician, a physicist, a scientist, and an engineer. There's 3 of them in the train. And they look outside the window. They find groups of sheep, black sheep. And the engineer first come up with a statement. He said, the sheep in Scotland are all black. It's because all the sheep they saw were black. So the sheep in Scotland are all black. The physicist, upon hearing this, the physicist says, he shake his head. The engineer asks him, what's wrong? He says, listen, how many sheep have you seen? You have not seen all the sheep in Scotland. How can you say that all the sheep are black? Okay, you can only see a few. So the engineer was a little bit taken aback. So he bowed his head down, and when he bowed his head down, his eye corner caught the side of the mathematician. The mathematician is shaking his head more violent than the physicist. So the engineer asked the mathematician, so what's wrong with his statement? The mathematician said, so listen, the correct statement should be this. We are traveling in Scotland. We saw a set of sheep. Okay, this sheep, at least one side of it is black, because you haven't seen the other side. How do you know the other side is not black, not white, or has pattern? Yeah, the statement that the mathematician made is correct, is very rigorous, and logically is also impeachable. But engineer and scientist is not that precise. In other words, so many of the time that I went to the mathematicians, I give a talk to the mathematics major. I always say that the part of the objective that I come here is to find a one-sided black sheep. Yeah. If I find a sheep that is one side black and other side is white, then I will agree totally with mathematicians. From that time on, I will follow their logic, rigorous logic discourse. Can we ask them to stop mowing the lawn? They can do some other parts and come back here later. It's intermittent. Sometimes better, sometimes. Yeah. We have to complain to the department, ask them to reschedule this lawn mowing or whatever, cleaning. Yeah. Because I get tired of competing with him. Can you listen clearly with this noise? Can you hear me?
Yeah, no problem. No problem.
So no problem. Yeah, okay. Yeah. All right. Yeah. I will not fuss anymore. Okay.
Okay.
Okay. So this is the first set of the difference. The second set of difference is the mathematicians are working in a very idealized space. Yeah. They, in their space, they are perfect. It's a perfect world. I can define anything I don't know. I can define. I can define distance. I can define all the interrelationship with functions, with whatever. Okay, and that space that I define, it's a space that everything is known. Yeah, at least the basic property is known. I can define, for example, a Banach space. I can prove a bunch of theory. Then I can change that into, say, Hilbert space. I change the norm of the distance measuring. I have a different space. I can prove theory. If I cannot prove one theory in one space, I can prove the theory in another space. I can change the condition. I can switch back and forth. Yeah, that's great. That kind of freedom we don't have. We live in the real space. In real space, our knowledge is incomplete and limited. Hello? Is that talking to me, or should I stop?
Yeah, no problem. Yeah,
no problem?
Thank you. And we have no problem.
No problem. Okay.
Yes.
All right.
I can hear you very clearly.
Sure. So with this real space and with this incomplete and limited knowledge, that forces us not to go absolute. Yeah. But this real space, we have to be consistent in this one word. And the mathematician can have inconsistency in different words. You can prove one theory in this space. It may not, that theory may not be true in other space. But do they care? They don't. Yeah. So I always say mathematicians are overly concerned with truth, with what is true, what is not true. But they have no concern of the truth. Yeah. What is the truth? I don't care. As long as it's within a logic, that's true. That's true. I can follow this logic and reach the conclusion. For example, you can ask the mathematician, there's two parallel lines. If I draw two parallel lines, and the two parallel lines, if it doesn't meet, I can develop a geometry. That's plane geometry. If two parallel lines meet, I can develop another set of geometry. That's non-Euclidean geometry. Okay? So if you ask a mathematician, say, does the two parallel lines meet or not meet? So I don't care. If you think it's meet, read the non-Euclidean geometry. If you think it doesn't meet, that's plane geometry. There's two different assumptions. Okay? Both can be true. Both can have very nice, beautiful theorem that you prove. So to them, whether it meet or not meet doesn't matter. In plane geometry, they cannot prove whether it doesn't meet. They say, well, that's an axiom. I define that. That's given. We cannot do that. We cannot say, well, given something, it has to work. So we have to have something that's work. We have to have something that's within the accuracy of observation. So the struggle, the conflict between reality and rigor has long bothered scientists. Yeah, it bothers me, and long before me, it bothered other people like Albert Einstein. And here's what Albert Einstein said: as far as the law of mathematics referring to reality, they are not certain, and as far as they are certain, they do not refer to reality. Thank you very much. You finally convinced him. This is much better, I think. The reality and rigor sometimes does not coexist. A line to mathematician has only one dimension. We can never find a physical line in the physical world. Any line you draw is perhaps not a line. It's just an approximation. Yeah. A perfect line appears only in our mind. We can define that. Yeah. A point, we can define that. Yeah. In the reality and certainty are very, very different things. And how was this data analysis done? In the past, most of the data analysis people are indeed the data processing people. You can go to any university, you talk about these people talk about data processing. Even sometimes they use the name data analyzing. Yeah. that they actually do. How did they do it? Most of the people in pursuit of the mathematical rigor and the certainty lost sight of the physics. I have the feeling that most scientists and most engineers are intimidated by the mathematician. From very young, we're taught, say, math is an important course. We have to do well. If we don't do well in math, forget it. You could probably will never go very far. So we are taught to accept the mathematician's rule, taught to accept whatever mathematician has done. So, and then when you look at the way that the mathematicians do their work, their research, they are very impressive. They're so rigorous. So we usually, most likely, will try to emulate, try to learn after them, try to follow their example. Yeah. So in pursuit of rigor and certainty, however, we lost sight of physics. We are also forced to idealize. We are also forced by idealize. That means in the natural world, we don't have the idealized space like a mathematician had. But in pursue that rigorous, in pursue that certainty, we try to make that follow them. By pursuing this, then we have to deviate from physics. And that most of that deviation, especially in the data analysis world, has dramatic consequences. Once we idealize, once we deviate from the physics, what do we have? Is that we have a world which is not real. But it's not totally unreal either. So we live in a pseudo-real world, a half-real, half-not-real world. And this real world and the not-real world, the division is not that clear. Yeah. And in that pseudo-real world, all processes are assumed to be linear and stationary. Because the linear stationary is what a mathematician can do. If you take that away, most of the method doesn't work. So we say, all right, we accept that. And I'll make an assignment for you to go to your library, whichever library that's near to you. Go to look for data analysis or data processing book to see which book does not make these assumptions. Yeah. And if you find one, let me see it. Okay? I'd like to see those books. And that is assignment for you and for your self-education or self-improvement. Okay? And this assumption has dire consequence. And what that is that you actually trim your feet to fit the shoes. So mathematician prepare a shoe for you, and your feet doesn't fit. Instead of saying, go send me another one, you just cut your feet off so that they can stack your feet in there. This is a Chinese proverb saying that 削足适履 means you trim your feet to fit the given mold. And nobody's that dumb. But metaphysically, we are actually doing that every day. Yeah, we assume this, we assume that just to fit the model. And this, of course, is no good. And mathematicians know that's no good. So the mathematicians are very, very smart people. They say, all right, we are that, you're complaining and says, look, I have to make this assumption of non-stationary data because most of the processes are really non-stationary. And how can I make it assumptions is stationary? Yeah. The stationary and non-stationary has a very clear definition. Yeah. Non-stationary has the most important consequence is if the process is stationary, we can do a lot of things. What do you mean by stationary? The easiest way to say that, other than the mathematician definition, the easiest way to say that is, if I measure something today, and I measure something tomorrow, and I mention something yesterday, and I mention something 10 years from now. They are the same. That's stationary. So mathematically, it means that is invariant under time translation. Yeah. You have t, you have t plus tau, and the property is identical. That's stationary. Many processes doesn't look like that. And if the process is stationary, you can do a lot of things. For example, average, mean. Yeah, we take average, we get mean. Mean means a lot. So what's the average value? People most ask. But if the process is non-stationary, mean is meaningless. A very simple example of non-stationary process is stock market. So nobody talk about the stock market. The average of stock market the last 5 years is, say, 500. That doesn't make any difference. Doesn't give any information, because the stock market goes up mostly, and not only goes up, it goes also up and down. Yeah, the simple average does not convey any information, does not give me anything. Yeah, so when the mathematicians know that they are non-stationary processes, but when they try to answer non-stationary process, however, they have to make assumptions. The assumption is that non-stationary but linear. And if that's the case, fine, we can do spectrogram, which is short-time Fourier transformation, and we can do wavelet analysis, which we have all kinds of various functions that will do analyze for you. And we can do Wigner-Weil distribution, and we can do all kinds of different things that to give you some feeling of non-stationary processes. But non-stationary, but linear. And then there are also people say, well, no, I'm worried more about the non-stationary. Sure, you can do non-stationary and non-linear, but the non-linear property has to be stationary. Yeah, there are lots of methods, like the phase space method, all this, are non-linear data processing. Data analysis, they even say. And you can actually go to see their books written for this. It's non-linear, but stationary. Why they are stationary? Because those people mostly will study chaos. Chaos is deterministic, not even random. You can run the chaos process, low-dimensional dynamic system. You can write it today, write it tomorrow, write it the day after tomorrow. It's the same. Yeah. Deterministic. You can write, I can write, it's the same. But most of the process, however, they are not the same. Yeah, it's not deterministic. It's random. Yeah. So we have linear but stationary, nonlinear, linear non-stationary, nonlinear but stationary and deterministic. So we know something about this too. But the real data we have is both nonlinear and non-stationary. For that, we don't have any method. Now, facing with that, what do? We apologize. The scientists and engineers learn to live, says, assuming the process is stationary. I don't know whether anybody has written papers. Most of the people are doing this. And in fact, I see more than one people come to me and say, yeah, that's exactly what we did. At the beginning of the paper, it say, assuming the process is stationary, or assuming process is locally stationary. This is a big thing in the mathematical community. Yeah, locally stationary. I don't look at the whole data. I look at the local area. If the local area is stationary, it's fine. Yeah. In fact, I remember once I give this talk in a very famous university. The senior mathematician, senior professor there, after he listened to my talk, he said, I don't care about what you talk about. I said, why? This is your method. I cannot prove theory. But if I make this local stationary, then it's good enough. I can write theory. I said, how? So he pulled out a manuscript, it's 60-page long, and it's make the assumption of local stationary. Yeah. Many processes may be locally stationary, but many processes may be not. Yeah. And most of the processes that I've seen are perhaps not. Yeah. If you take any random walk or whatever, locally they have strength. It's not going to be stationary. Yeah. Globally, maybe, yeah, if you have long enough data. So this kind of, even sometimes nonlinearity is weak. Yeah. This kind of assumption, once you state that, then the reviewer will understand that this guy knows what he's talking about. Yeah. Publish your paper, let your paper go through, and let your paper get published. But we can assume all we want. The assumption is not going to change the reality. Yeah. The process, if it's not nonlinear, it's still nonlinear. It's not stationary, it's still not stationary. This kind of practice is done day in and day out. I summarize this syndrome as close your ear and try to steal a bell. If when you steal a bell, the bell makes noise. So you plug your ear, you don't hear the noise, you think other people will not hear it. Other people hear it. Other people actually see it. Yeah. So it's this kind of mistake, it's this kind of syndrome that we'll try to change. Yeah. The real world is different. Again, I cite Albert Einstein. Albert Einstein is, of course, everybody know him. He is famous for scientists, and in fact, a lot of people think he's a mathematician. Yeah. He will use whatever is not there, he will use it. Yeah. Is he a good mathematician? There are stories talk about that. Albert Einstein will have to use differential geometry to describe this time warp and space warp. He has difficulty. He found his good friend, a mathematician, to help him. And the story goes that Hilbert, the famous Hilbert, David Hilbert, once made such a statement. True or not true, I don't know, but I read it. So Hilbert said that Einstein is really a poor mathematician. So I can go in the town of Göttingen. I can drag any young boy and ask him, they know more about the differential geometry than Albert Einstein. But he found the relativity. We don't. Yeah. You may know a lot of math, but you may not know how to use it. It's Albert Einstein matched him. But when in his struggle, he finds the mathematics are well and good, but nature keeps dragging us around by the nose. So nature is very different. They do not follow your assumption. If you made this false or half-false assumption, sooner or later something is going to happen. And that will happen will actually prove you totally wrong. The reason that I get into this is that whatever processes that I've seen are mostly non-stationary, are mostly nonlinear. And not another interesting thing, and it's actually inescapable thing, is that the data that I got is invariably too short. I've never get the data start from minus infinity to plus infinity. Yeah. If you do a Fourier transformation, for example, the theory requires the integrate from minus infinity to plus infinity. And probability means that if your population is infinite. We don't have that. Yeah. We have finite time, finite population. So, and not only that, most of the processes are not repeatable. We cannot do the truly ensemble average. Mathematicians know that if we have a stationary process, we can do time average. So if you do not have stationary process, you do ensemble average. What's the ensemble average? You repeat the experiment. Yeah. In the laboratory, you can do that. You roll a ball on a slope. You see how long it fall, how far it roll. And you can repeat this and repeat 1,000 times, and then you get a mean. That's good. Yeah, that means you can repeat. Can we repeat 1,000 of times? This is well, now this time we're not going to invent automobile internal combustion engine, so that we don't have cars, we don't drive. See whether the global temperature will increase or not. You cannot do that. We only have one shot. So many of the ensemble is not possible. temporary mean may not be meaningful in this case. So the ergodicity assumption is out. A lot of the methods that the mathematician told us were useless. Well, not useless, were at least not usable. So under this condition, we have to find something new. And what's the something new that we're going to look? My guiding principle is this. This is Richard Feynman. Richard Feynman said that the job of a scientist is to listen carefully to nature, not to tell nature what to do, how to behave. Yeah. How can you listen to the nature and understand the nature? You have to know their language. You cannot go in there and say, so I only have my language. Nature is highly variable. It's all the phenomena, all the events there. Not only that, just take a simple example. Say, if I don't speak Japanese, I come to the group of the class. I insist on speaking Chinese. Nobody understands me. And they can say something in Japanese. I don't understand. We cannot communicate. How can we understand them? We have to know their language. Now, in this particular case, we use a common language. Everybody understands English. Yeah. So if you want to understand somebody, you have to know their language. Nature has their own vocabulary, their own expression. Yeah. It's not that you go in there and say, I don't care, I only have Fourier analysis, or I only have the standard probability theory. Yeah. I give you a little bit introduction of that part at the beginning of the, when we do the holding pattern, we give you a little bit inkling of that. It's not enough to describe the complicated natural setting. Yeah. So we have to understand the nature in their own way. You cannot disturb them. Last January, after attending the American Mathematical Society annual meeting in San Diego, I made a stop at Pasadena. I give very similar talk, introduction talk, that I'm giving today to Caltech, at Caltech, the Applied Math group. When I show this view graph, there's a big stir in the audience. One of the reasons is that Richard Feynman is a big icon in Caltech. He's so famous, so well known there. So when I mention his name, of course, people get emotional. But that time, this emotion is get beyond common reaction. So I asked him, what's wrong? So everybody's head turned around and point to a lady. She said, that lady is Richard Feynman's kid sister. Richard Feynman's sister. So I look at her and said, oh yeah, Richard Feynman's sister. It's my honor to know you. So she stood up and made a statement. She says, I have never heard my brother say this. I was almost embarrassed, but then she said, but this sounds exactly like him. I believe he will say this, even though not in front of me. Yeah, I know exactly where this come from. I can find where I quoted from. But then she really helped me. She said, yeah, I think this is exactly what the way that he's thinking about things. She was so much enjoy this quotation. At the end of my talk, their question and answer session, somebody asked questions. Then she jumps up. She said, no, let me answer this. I know exactly how to answer. So she turned around to that person and said, think what my brother said. Listen carefully to nature. You have to use their language, not your language. Yeah, and that solves lots of problems. Yeah, and later we had lunch together, and we had a very pleasant afternoon together. Yeah, so we have to listen to nature. If we want to be a good scientist, listen to nature carefully. It's important. Yeah, not impose anything on that. And how you can listen to them, not impose on them? You adapt. We all adapt. If we do not adapt, we'll still be single cell, swimming around. We'll never have math. How you adapt? You learn their language. Like if you're in Japan, you learn Japanese. In China, you learn Chinese. You go to America, you learn English. Then you'll be able to understand other people. You don't try to go everywhere, just speak one language, like most of the Americans do. Yeah. Anyway, so usually at this time in United States, I will be stopped long before I reach here. I will be stopped. People ask, "You use the word nonlinear so freely, yeah, and can you tell me what do you mean by nonlinear?" Nonlinear, linear, nonlinear has a very rigorous mathematical definition. That definition is from a system point of view. From engineers talking as a system point of view. From mathematicians, they say, well, the linear space, I can define a bunch of linear equation, linear operator, linear algebra. If it doesn't fit that, it's nonlinear. Nonlinear has very poor definition. It's just, if it doesn't fit this, it's that. It's qualitative, not quantitative. Yeah. Now, how do I use? Say, based on linear algebra, we have input-output. Yeah. But in reality, many of the things that we study, we don't have input. We don't know what the input is. Yeah. If we're lucky, we have part of the output. We don't have the total output. Yeah. So how can we discuss nonlinear problem? Now this is what I want to make clear. Throughout this whole class, we'll talk about data. How can we tell whether the data is from linear or nonlinear processes? To do that, we have to go to the basics. The basics is a nonlinear differential equation. If I write this equation, if I take that term away, take the red term away, then we have a linear differential equation. That's no challenge to anybody, or not anybody here. Okay, you can solve it. But if I add this term, that equation has been here more than 100 years. Few people know exactly how to deal with it. So I'm not going to try to solve this equation. I'm trying just to tell you what's going on. If I factor 1x out, then what I have is 1 plus epsilon x squared. That's equal to gamma cosine omega t. Yeah. So this, consider this as a coefficient. I have a linear oscillator. But this coefficient can be my mass, can be my spring constant, can be all kinds of things to behave in this nonlinear differential equation. But unfortunately, this coefficient is not a constant. This is a variable. Not only it's a variable in such a way that it's changing with the dependent variable. That's what we call nonlinear. As I said, I don't want to solve this equation, but I want to have a closest, the nearest analogy of this system. This system, if epsilon equal to 0, then I have a linear system. Linear system is a single pendula with very small angle, simple pendula. That simple pendula, the frequency is constant. And that constant frequency is being observed by Galileo. Galileo died the year Newton was born, so he doesn't know differential equation, doesn't know even calculus. Yeah. But he finds the pendular frequency is constant. How did he did? He used his pulse to see how the chandelier in the church swing around. And obviously he's not very attentive to the masses that the priests are celebrating. And that's how he get into all kinds of trouble. Anyway, he find that if the simple pendula, the frequency depends only on length. But now we know, if we measure our pulse, we find the pulse is highly variable. Yeah, that's a different story. But that's close enough, let's say. Yeah, close enough. So it's close enough that he deduced this law. Says, okay, pendula, the frequency only depends upon length. Now, If we put this term in, what happens? The length is not constant. If epsilon is positive, as the x increases, the length, this term we use as a length, increases. If epsilon is negative, this term decreases, the length decreases. So we have a pendulum, either move this way or move that way. It's no longer a simple pendulum. This is a nonlinear pendulum. In this nonlinear pendulum, the frequency is different here from there. So everywhere, the frequency is different. Within one swing, the frequency keeps changing. And this I call the intra-wave frequency modulation. That means within one swing, the frequency keeps changing. What happened? If you within one swing, the frequency change, the consequence is a distortion of I forgot a view graph to show you the shape. The consequence is shape is no longer sine wave. The shape becomes highly distorted, becomes a nonlinear wave. The people call that nonlinear wave distortion or harmonic distortion or whatever name. Yeah. Now, if frequency change from place to place, from time to time, and we want to describe that event, how can we describe it? I immediately think, why don't we use Hilbert transformation? Hilbert transformation is a simple operation, but it involves a singular integral. The singular integral means that if I have x belongs to LP class, that means I raise to p's power, I can always integrate, it converges. That kind of function, then I can do this integral and take the Cauchy principal value, I get a y. Then this x and y form an analytical pair. That means it satisfies Cauchy-Riemann equation and all that. It's very nice. If I can find this y and x and y then form an analytical pair, then I can write into a complex form. So x and y is complex, then I can write it as a and ei theta t in the polar coordinate. See, complex number has two ways to represent it: real, imaginary, or polar coordinate. Yeah. So if I write in the polar coordinate, I got a beautiful expression. Then I know exactly how the amplitude change, and I also know exactly how the frequency change. Yeah, and I know everything now. This is just unbelievably nice. See, for example, if I have the data given in this blue line, the blue curve, yeah, and if I will use Hilbert transformation, what I do? At this point, for example, my amplitude is small, my period is also small, but I use only that point. At that one point, amplitude and period. I don't use the whole sine wave. If I use the whole sine wave, it becomes Fourier. I only use that one point. If I change a point, then my amplitude change, my period also change. So this amplitude and period change give me description of that data at any instant. The amplitude and frequency all change. Such a nice transformation invented by such a famous mathematician. Why people don't use it? That's my first question. By the way, David Hilbert is no doubt the greatest mathematician in the late 19th century and early 20th century. And he probably will be one of the greatest mathematicians ever. One of the greatest mathematicians ever. Hilbert transformation, however, is not one of his greatest contributions. And in fact, he has never written a paper called the Hilbert transformation. Hilbert transformation appears in footnotes in his study of Fourier analysis. But it's very useful. And the useful in a way is that we don't have to apologize anymore, I thought. We can take this Hilbert transformation and and actually just analyze the data. And if we know the amplitude, if we know the frequency, then we can do the deal with the even intrawave frequency modulation. And if we can deal with intrawave frequency modulation, then we can deal with many other things. Yeah. So why didn't people use it? There are problems. So mathematicians told us Hilbert transformation exists for any LP class of function. Yeah. So I just take this very simple example here. This simple example well, it's all right. Okay. Well, it's still invisible. Anyway, this is the data. This vertical axis is the time. Horizontal axis is also time. What this data is the length of day. Our day is not exact 24 hours. Our day varies from one day to another. How does it vary? Because our rotating speed of the Earth is not constant. It keeps changing a little bit. And if we define a day by the rotating speed of Earth, then each day is different from the other. That varies. And over the last 40 years, from 1962 to 2002, all the way here to 2002, there are about 40 years of data. And these 40 years, each day is 365 days plus or minus a quarter. We will have 14,000 data points. And that data points plot out to the day fluctuates. The length of day fluctuates like this. Yeah, we'll come back to this data later. And this unit is 0, 1, 2, 3. And that's all in milliseconds. It's very tiny. Millisecond, 1,000th of a second. Is that important? Yeah, it is important to some space application. That's why in NASA, one of my colleagues assigned to keep track of this. Actually, more than one person was assigned to do this. For this data, if I do a Hilbert transformation, what I got? I get this mass. When you look at this mass, you can immediately draw the conclusion that this gives you no information because it's so random, so chaotic. Yeah, anything so random, so chaotic cannot have meaning, cannot have a lot of information. The information content is almost zero. Yeah, so that's no good. So this is Hilbert transformation. This axis is real. This axis is imaginary. Yeah. So you have a jumble of random curve. It almost looks like a plate of spaghetti. Yeah. And if I compute the phase function, the phase function looks like this. It jumps. It oscillates a little bit, and it will come to here, suddenly jump. It come here, suddenly jump. And these jumps are not random, totally random. Each of the jumps is 2 pi. Now you can go and measure it. It's 2 pi. So there are, if you look at this data in detail, you find that within even that the small varying part, there are lots of structures. And if you expand the small part of this, there are again other oscillations. There are oscillation inside oscillation. In fact, Michael Berry, a professor in physics at Bristol University, has studied this phase function of a random number. And in fact, he finds that the phase function of a wideband white noise. Wideband white noise means infinitely long. Okay, we don't have that, but theoretically, to the limit you have infinite long white noise, the phase function approach to Weierstrass function. Weierstrass function means everywhere continuous but nowhere differentiable. Yeah. But otherwise, because this scale inside another scale has certain self-similarity. So Michael Berry proved that the phase function of a random number most likely is fractal. Yeah. So if it's fractal, if it looks like this, can we use it? Mathematicians told us that the Hilbert transformation exists for all the functions. So if we have this, we can always find the amplitude. We can always find a phase function. Then, by definition, time derivative of phase function is the frequency. So we just take the phase function and take the derivative. And the derivative come out to be like this. And this is 0. It has equal opportunity to be positive and then negative locally because it's oscillate. Any upswing give you positive frequency. Any downswing give you negative frequency. So the frequency is both positive and negative. Is this information useful? It's not only it's not useful, it's really harmful to Hilbert transformation. Because of this, many people say, well, Hilbert transformation is useless. But there are other side of the coin is that a lot of people actually think this is the solution. And the person think that the solution is Hahn, H-A-H-N. He did publish a paper. It's called the Hilbert transformation and its application in data analysis. Yeah. If you take that book, you will get this answer. And this answer is useless, as I said. Why it is useless? Why the tradition doesn't work? And here, I have 3 curves. These are 3 curves. This blue one, this is my 0 line. The blue one is a sine wave. A sine wave, just a sine wave. And this green one is the sine wave plus 0.5 of the amplitude. So the center line get moved a little bit. It's not symmetric with respect to 0 anymore. And then I move it further to here. That means 1.5, more than its amplitude. Then even the 12 is beyond that. So I have 3 sine waves. They're all sine waves. So if I do a Hilbert transformation to these 3 sine waves, what I got? I get 3 circles. The blue circle is centered here. The green circle is centered here. The red circle is centered over here. So Hilbert transformation gives me 3 circles. That's fine. That means it looks like a sine wave. But based on this, if I take the phase angle, then the phase angle will be very different. Does it work now? Yeah. It still doesn't work. Oh, it works. Work better now. Yeah. If I try to find the phase function of this, then what I do? So from this point, my phase angle is this angle. And if I go through all this point all the way to there, my phase angle is that. After this point, then the phase angle decreases. In other words, the phase angle following this, the phase angle decreases. And after this point, it increases. But it just varies between these 2 limits. It will never go beyond 2 pi. Yeah. So if I plot the phase angle of this 3 circle, for the blue one, I have a straight line. For the green one, because I have an eccentric circle, the eccentric circle goes like a VV line going through like that. And the red line for the circle that's way beyond the 0. The red line go up and down, but never go beyond 2 pi. So I have 3 different phase functions. If phase function derivative is the frequency, then I will have 3 different frequencies. For the blue line, I have a constant. For the green line, because it's a VV, I sometimes have a large value, sometimes a small value, so it's go up and down, up and down, up and down. And for the red line, it's go actually drop all the way to negative and bounce back and negative bounce back, negative bounce back. So we have negative frequency. Negative frequency in general is very difficult to attach physical meaning to it. Even if I accept the mathematician's definition, negative frequency is the same. Okay, that gives me both positive and negative frequency. Fine. But what is not fine is that for one simple sine wave, I can get the three values. This is the three arbitrary position. In fact, I can move this sine wave to different location. I can have any number I want. And that's very unsettling. How can I have one sine wave I get all the number I want? The only right number is this. This is the constant frequency. And the green line is still right if I average exact one wavelength. I still get it right. But if I miss that exact one wavelength, then I will not have it right. So this is something that we cannot accept. So obviously, if we use full Hilbert transformation without any modification, it's not going to work. Okay? So we have to do something different. And that something different will start from next time. Okay? We'll stop here. The something different is what I will introduce to you in this class. Because in Japan, we can only the lecture period is limited to 90 minutes. We have to stop. We still have a little bit time. You can ask questions. Do you have any questions from Tokyo?
So, the student, do you have the question?
Anybody has a question from Hiroshima? Question from Taida? A question here. You can hear me all right, do you?
Yeah, so perfect.
Okay.
The voice is very clear.
All right. Thank you very much. Yeah.
Yeah,
so
thank you.
If you have any question, please ask. If not, you can be excused. Well, I was told that you will only have 90 minutes over your side. After 90 minutes, they're going to cut off the transmission. Yeah. So from now on, we will just lecture around 90 minutes, and I will stop. Okay. I may stop 5 minutes early for you to ask any questions. If you do not have any question, right now, you can think about the question and ask me the next time. All right?
Okay.
All right. How about Hiroshima side? Do you have any questions?
Yes.
Can you hear me clear?
Yeah, it's perfect.
Okay. Thank you very much.
Yes, thank you.
Yeah, and Taida, National Taiwan University. Can you hear me? National Taiwan University is not on today, huh? Yeah, can you hear me? Their microphone has a problem.
Yes, we can hear you. We don't have any question.
Okay, thank you very much. Yeah, and Yang Ming, is Yang Ming on today? 连线的. That's all right. So this is Jing Yi. Jing Yi has any questions? Jing Yi? Okay. Jing Yi is always very quiet. Do we have any question here?
Oh, so far so good.
Hi.
Hi.
Okay. That's all right.
Okay, so far so good.
So far so good. Thank you very much.
Yeah, thanks.
Yeah. All right. So I'll see you next week. Well, not next week. Friday. See you Friday.
Yeah, see you Friday.
Okay. Bye-bye.
Okay, thank you very much.
Right, thank you. Do you have any? Yeah? Okay, bye-bye. Do you have any questions?
Complex, then what happened?
From side, the question is coming. I think someone is asking a question.
Someone making a question?
No.
From which part and then
Okay.
You use complex number, not use complex number, then what happened?
Pardon? Our data, by definition, here is a time series. It's all real number. And the reason that we want to convert it to complex number is try to get its amplitude and try to get it phase function. Yeah. And later we'll get into discussion. You'll find that to get the amplitude and the phase function is not that simple. Yeah. That's why we have to spend the whole semester to talk about it. Yeah. But the short story is that you can do a little bit very simple things after I go through the introduction. You will be able to actually get a very good solution using Hilbert transformation. Yeah. The complex number, we need a complex number just because we want to have the phase function as function of time and amplitude as function of time. Yeah. To describe the non-stationary, nonlinear processes. Any question here? You should have no excuse not to understand me. And if you have any question, please ask. All right, they're going to be off the air 90 minutes now. Okay. If you don't have any
questions. Thank you very much.
Okay, thank you. Bye-bye.
Thank you very much. Bye-bye.
Bye-bye. All right. To be fair, we should not stay here too long because otherwise we have unfair advantage over them. 没有问题啊. Now they are off the air. We can speak Chinese. Relax. 有没有问题?
Hello?
No, 它不是一半是 amplitude. Hilbert transformation actually all we look for is a phase shift. 原来一个 sine function， 我只要把它 phase shift 就变 cosine，sin cosine 呢，我就可以有 sin 有 cosine， 我就可以找它的那个 amplitude 跟 argument， 跟它的 phase。其实 in fact we don't have to do that. Later I will teach you how to do that without Hilbert transformation. Okay. Initially, that's how I get into it, like I explained at the beginning of the course. But later I find that the Hilbert transformation is not really help me a whole lot. Sometimes it's actually cause problem. Yeah. So I'm drifting away from Hilbert transformation. But the names get stuck, so I cannot change that anymore. Okay. All right. No more question?
Hello.
All right then. Thank you very much. Yeah.
现在可以问吗？